Thank you, Pei, for the introduction. Hello, everyone. Today I'm glad to introduce our work. It's called DeepAPP, a deep reinforcement learning model for the mobile app prediction. My name is Wan Du. Now I'm working at UC Merced. This is a collaborative work with my colleagues from Xi'an University. The two authors are students and they cannot come here. So I will do the presentation. So nowadays, every one of us install a lot of apps that on our computer, on our mobile devices, and within a very short time, like 5 minutes, probably we will use several apps. So the question in our paper we want to ask is that can we predict the applications that a user wants to use in the next 5 minutes? This is a very important question to ask because if we can do the prediction, actually we can load the applications beforehand to save the loading time and improve the user's experience. We can also give some suggestions to the user, like this one, and the user can find the applications she wants to use quickly to save the time to search for the proper application. So the most commonly used method to do the application usage prediction is based on the most frequently used app. So like Siri, Apple suggests that the most important, the next applications that the user will use is based on the most frequently used application. So it is easy to implement because if you have the historical data, you just need to find the most frequently used app. But the problem is that this method does not consider the context information. This is the result from our data. We have more than 400 users' data for 3 weeks. And we have plotted the probabilities of the user to use a kind of app based on different context information. For example, if the user is at home, normally the user will play some games or use the social media apps. But if it is at work, so the user will use the browsers a lot. Okay, so we need to consider the context information when we do the app prediction. So there is a work, an existing work that has already considered the context information. The context information in this work is simply like the home and workplace. And it also considers the current time and the current apps that the user is using now. But the problem is that the context information like home and work is very simple. Another thing is that this work does not consider the launch time. Launching time here we mean that when the user will use that app. It is also an important question. Why? Because if we predict that the user will use an app later, but if we don't know when the user will use it, actually it's useless. Why? Because if the user will use this app in an hour, but if we preload this app beforehand, like 1 hour, we will occupy the memory cost, right? So we want to just have an accurate prediction of the launching time, so we can preload the app that slightly before the user uses it. So there is also an existing work that has already considered the launching time. This work that predicts first find the next app that the user wants to use, and then based on this result, this work will estimate its launching time based on the historical data of that specific app. Okay? But the problem is that this paper does not consider the context information. So this is pretty much what we have now. As we see that there are two important limitations. First is that the context information. Another one is the launching time. And in this work, we also found another important observation, is that when we want to do the application prediction, actually, we want to predict what apps that the user will use in the next time slot, like in 5 minutes. So in these 5 minutes, the user may use multiple apps, but not just one app. So we want to predict a combination of apps. Why? Because, for example, in this example, we will predict the user will use PayPal to pay something, or the user will use Amazon with a different probability. But if we can predict that the user in the next 5 minutes, she will use a combination of Amazon and PayPal, actually, we can increase the accuracy of our prediction. Why? Because it's highly possible that the user, if the user used Amazon, she will use the PayPal to pay her bill, right? So we want to do this combination, a prediction that can combine all the possible applications that the user will use in the next time slot. How to do it? So we provide DeepAPP. It is a deep reinforcement learning model for the application usage. So let me first introduce the key component in this model. So we have, in this model, we have the environment. Environment actually is a smartphone of the user. And then we have an agent. An agent is a neural network. It takes the state of the smartphone. The state actually is the current applications that the user is using now. And then the current time and the current context. We put all the state to the neural network. The neural network takes the state as the input, and then do the prediction. Suppose that we have already got a policy, okay? And then based on the computation in this agent, we will get an action. The action is a combination of all the possible applications that the user will use in next time slot, okay? So, and then we have this policy, right? And then we give the action to the environment. We say that we tell the smartphone, oh, the next 5 minutes the user will use these two applications. Based on the results, the smartphone will provide some suggestions to the user. And in the next time slot, the user may use the applications that we have predicted, may not, right? So this is the feedback. And then based on the behavior of the user, we can get a reward value. This reward value will be input to the agent. The agent will use this reward value to update its policy. That means it will update its weight of the neural network. Okay, so this is the reward function. Okay, so if we suppose that now we have a neural network already, we have already trained the network. Okay, so now the workflow of our system is very simple. We have a mobile phone and we have a trained neural network. It is an application prediction agent. Okay, in the agent we have the input and the state, and we have the actions, and we also treated the reward function to do the agent updating, right? So at one moment, the user on the smartphones we will have the context-aware module, right? This module will sense the context of the user. And for example, the current time, the current application the user is using, and the locations of the user, and the surrounding environment of the users. And based on the context information, the agent will treat the context information as the state, and then use the policy to do the prediction. Then we will get the prediction results. We call it action. Now we have the prediction result, like what apps that the user will use in next time slot. And then we use a user interface to provide our results to the user. And then in next time slot, the user will use it or the user will not use it. But based on the feedback from the smartphone, actually we can calculate the reward and update the agent policy gradually. Okay? So now this is the workflow of our system. I would like to emphasize is that the agent this one, this is a neural network. It can run on a server. It can also run on the smartphone because it's a very simple neural network. And what we need to use this agent is just to do one inference. So the inference is very lightweight. So we can run this agent actually on a smartphone. Okay, so this is what we want to do. So we first implement a DQN networks and do the application prediction. And DQN is a commonly used deep reinforcement learning model. And we do the experiment on a laptop. And this is the hardware we're using with a 8-core CPU. And we first try to evaluate the performance of this system. And we suppose that the user has installed 20 applications on her smartphone. 20 applications actually is not a lot, right? Normally we install hundreds of smartphones, applications on the smartphone. So we just use this simple example to do the evaluation. Okay? So the user installed 20 applications. So what we need to predict is a combination of all the possible applications that the user will use in next time slots, right? So the combination, different possible combinations actually, the number is a lot. The user maybe in the next time slot, the user will not use any apps. And she may use just one app from the 20 apps, or she will use all these 20 apps, right? If we add up all these possible combination results, actually we can have more than 1 million possible actions we need to choose. So this DQN network needs to evaluate all these possible actions. How to do the evaluation? Actually, the DQN network needs to calculate the Q value for each possible action. It will take the laptop to more than 2 seconds to do the calculation. Okay? It is too slow. Why? Based on our data, we can see that we plot the shortest time interval between 2 application usage. And this is our data. It's more than 400 users and for 3 weeks, right? From this CDF figure, we can see that more than 95% of the users, that actually they switch from one application to another one within 2 seconds. That means we need to do the prediction very fast within 2 seconds, right? So yeah, we need to do the real-time application prediction. So what do? We propose that we use a new architecture. It's called actor and critic networks. So it is the idea. The main idea is borrowed from computer vision, and this is an actor neural network. It is almost the same as the DQN networks, but the key difference is that the output of this network actually is in continuous space. So we do not need to verify every possible actions in discrete space. So because the output is continuous space, so we can only do the verifications within a very short, small continuous space. So actually the prediction with these actor networks is very fast. But the output of this network actually is in continuous space. So we need to decretize the output into some possible actions that we can implement on the computer, like a combination of all the possible applications that the user will use, right? So we will have a set of actions that we can choose. So based on the set, we will have another critic network. This network will choose from the set to find the most likely action that the user will use. So this is a rough idea of this architecture. And now we can do the fast prediction. Can we run this system on the smartphone now? No, not yet. There is another challenge about sparse applications usage data. We don't have sufficient training data. Let's see this example. Okay, the x-axis is a time slot. One time slot is half an hour. So this figure is 24 hours, is 1 day. Okay, and the y-axis is the application ID. We can say for one user for 7 days, actually the user mostly use these applications, right? For the rest of the applications, actually the user rarely touch them. So if we have the training data from one user, like this one, and if we train a model for this user based on this data, actually the training data is too sparse, and we need to accumulate the training data for a long time, like multiple years, so to do the prediction, right? So what we do is that we propose that we first generate a general model. This general model is based on the training data of all the users. We have like 443 users. This general model will catch the application usage behavior of all the users. This behavior is some common behaviors, right? So now suppose that we have a general model. This is a general model we have, and we can use the general model to do the prediction. For example, at this moment, we do the prediction, the user will use the message application. Oh, we are right. So, and then next time it will use Google Store. Oh, sorry, we are wrong, right? So this is the general model we are having now. Okay, and then we download this general model on the user's smartphone, and we try to train a personalized agent for each user. And for example, for this user, we divide the time into different time durations. For example, in our implementation, T is 1 day. Within 1 day, we use this general model to do the prediction. And this is different prediction cases, right, for different time slots. We can have a lot of predictions within 1 day, right? Sometimes we are right, sometimes we are wrong. Right? We put all the prediction cases in a database. We call it a memory. And then we choose from the memory a batch, randomly choose some prediction cases. And we form a batch and do the updating of the new agent. Right? We use the data, randomly choose some data from the prediction cases results. And then we use the data to form a batch, and then we update the agent, right? Because here we have the prediction results, right? Whether we are right or not. So this information can be used as a reward to train our data. So now, in the next day, in the first day, at the end of the first day, we update our policy. And then the next day, we will use a new policy, right? And then we will do the prediction. We will receive more prediction cases. And later, we will update our policy day by day until that our policy becomes stable. Okay, so this is how we develop our personalized agent for each user. Okay, now we have solved the fast prediction problem and the sparse training data problem. We still want to consider all the complex context informations in the prediction. As we know that it is obvious that when the user is using an app, it is determined by the location, right? Whether the user is at home or at work, or he is in a park, right? But it also depends on some hidden context, right? Whether the user is doing some access or whether he is in some special locations, right? So even some context that we do not know, and or we cannot explicitly describe all these contexts, right? So we want to consider all the complex context informations in our prediction. So we need to have a state representation method. What we do is that this is a particular case in our work because we have the cellular data. We know the rough location information of the user as the cell tower's location. For this cell tower, we can have a point of interest distributions, like the surrounding buildings within around this cell tower, like the airport, the train station, and a lot, right? We will treat all these POI distributions within a vector. In addition to the time and the current app that we are using now, to treat all these information as a context to do the prediction. Okay, so now we have developed the system. We evaluate the system with our sensor data. We use 2-week data to do the training and 1 week for the validation. So that we have done a set of experiments to evaluate the prediction accuracy. We also evaluate the evolution of the prediction accuracy of our system because we update the personalized agent gradually. And we also do the evaluate the performance gain of the 3 proposed techniques separately. So here I just show the overall accuracy. And compared with the previous works, this is the latest work published last year. And we can say our system can improve the precision and recall of the application prediction by more than 8% and 15%. And we can see that if we use the decoding method or if we use our actor critical architecture, actually these two systems actually have the same accuracy, similar accuracy. Why? Because they are both deep reinforcement learning based method. But if you use our system, the new architecture, actually this is our new architecture, and we can reduce the prediction time by more than 6 times. So that means that we can do the prediction very fast. Finally, we implement our systems on smartphones and do some field study. And we recruit 29 participants and do the experiment in almost 2 months last year. And we want to evaluate the accuracy of our app prediction, and we also want to verify the real user experience. And here I show the results of the loading time saving. We can see here more than half cases, right? More than half cases that actually we can save the loading time by more than 20%, right? This figure is a prediction time. We can say we can make the more than 80% of the predictions within 1 second. Okay, in conclusion, in this work we have developed a deep reinforcement learning model for application usage prediction. There are 3 challenges if we implement the DRL system for application prediction. And we propose 3 corresponding techniques to solve these challenges, and we do the experiment on the field study. Finally, we have released the code and the part of the data set. So if you are interested, please check on my website. Thank you.